Okay, so I can't talk over you. So we had a question and you guys can all benefit from watching and listening. Okay, so when we talk about these digit problems, the fundamental thing that you need to understand is that every 2-digit number is made up of what we call units or ones value and our tens. If we had a 3-digit problem, we could be talking about our hundreds place value and so on that way. So we're talking about a certain 2-digit number. And what I need to know is, and give yourself a sample here just to think of. Somebody give me a 2-digit number, make it up quick. 27. So if 27 is my 2-digit number, 2 and 7 are the digits. But the value of this number, this is actually worth 20 and this is worth 7. That's how you get 27. So this digit is actually multiplied by what it represents. I have 2 sets of tens. So in an algebra problem, I need to define my variables and I'm going to make this X and this Y. So when I'm talking about the value of my digits, every X is going to be worth 10. And every Y is worth 1. So when I'm talking about the value of my numbers, my X and Y represent my digits, but their place in the number, I have to remember this X is not worth the digit. It's worth 10 times that digit. Same as if I had a hundreds value, this digit, let's say I called this one Z, God bless you, that would be worth 100 Zs. So when I go to write the problem, the tens digit of a 2-digit number, here's my tens digit. So my tens digit is 1 more than 3 times my units or my ones digit. So that's my first equation. Every time you're solving a system of equations, you need as many different pieces of information as unknown variables. 2 variables, you need 2 equations. 3 variables, you need 3 equations. You can't solve it if you don't have enough of that information to weave together into some kind of a system. That's my first story. As soon as I start talking about my original number, here's the value of my number. So when I go to write my second equation, it says your original number. Well, my original number is 10x plus y. So the original number is, every time you see the word is, that's your equal sign. 9 less, that's one of those ones that translates backwards. Remember that? 9 less than 3 times the value when you interchange. So if you interchange the numbers, you flip-flop. So if my original number is 10x plus 1y, my value of my number when I change that, my swap, means that my y's are in the tens place and my x's are in the units place. So when I talk about 9 less than 3 times the number formed by, this number formed by interchanging the digits is 3y or 10y plus x. So here's my original number. And this is the number that I get when I flip-flop the digits. So when I clean things up a little bit, 10x plus y is equal to 30y plus 3x minus 9. Group my x's and y's. So I'm going to call this 7x is equal to 29y minus 9. So when I solve a system of equations, I have 2 choices, substitution or elimination. This one naturally leads towards substitution because I already have x solved for. So I'm just going to go ahead and instead of writing x, I'm going to write what I know x is equal to. And then that gives me Now I've written my equation in all y's. So I can say that 7 plus 21y is equal to 29y minus 9. So I get, add 9 to each side, 16, subtract 21y's from each side, 8y. So my y value is equal to 2. The easiest thing to do now is take this value for y and plug it in here. So my x is equal to 1 plus 3 times 2. So my x value is equal to 7. So my original number is going to be 72. And my number when I flip-flop the digits is going to be 27. And I can go back through and I can make sure that I know that my 10th digit is 1 more than 3 times my units. That works. The original number is 9 less than 3 times this. So multiply this and add, right? And see if that works out. It should work out. Does that answer your question? Which part of it was tricky for you?
I guess just wording of the problem.
Anybody else struggle with one that they want to see? Was there an answer? Yeah? 5 on the same page? Or money problems. So the money problems. So you think that you're not loud when you're talking while I am, but you kind of are. Because it makes it hard for us to all focus. All right, I found a bag of coins worth $1.18. That sentence there is all you need to write your first sentence, because you know that every quarter is worth 25 cents. You know that every dime is worth 10 cents. You know that every nickel is worth 5 cents. Every penny is worth 1 cent. And you know that together, whatever you found adds up to $1.18. So every time we deal with money problems, we teach the kids to go ahead and multiply everything by 100, because it's so much easier to not have to deal with that decimal place. Everybody okay with that math so far? All right, so then we dive into the problem and see what it is we have. We have no dimes. So right away, no dimes are a part of the problem. So the number of pennies you have is 13 more than the number of nickels. And the number of nickels is 2 more than the number of quarters. And you want to figure out how many coins you have. So remember I said, you need a piece of information for every unknown variable. So if I have no dimes, I have 1, 2, 3 variables. So I have this and this and this. I've got 3 pieces of information, 3 variables. I'm good to go. I can find an answer for this one. If I do substitution, I have to make sure that I can communicate everything in terms of one variable. So I look at the problem and I try to figure out which one variable does each piece of information all have. Do you see how they all have an N? They don't, this one doesn't have a Q, right? This one doesn't have a P, right? This one's got it all. But I have to figure out which one is in common for these ones. So that's my first step, which means I'm going to write this entire sentence in terms of N's. So when I want to figure out what I'm going to write for Q and what I'm going to write for P, I might end up having to do a little bit of switching around. So I can just go ahead and write 13 plus N in here, no problem. But this is a little bit of a problem. So I need to subtract 2 from each side. And now I know if Q is equal to N minus 2, then I can write N minus 2 instead of Q. So now I've got 25 N's minus 50 plus 5 N's plus 13 plus N, and that's equal to 118. So then I just keep going, solve for N, and then I can figure out how many quarters, nickels, and pennies I have. Sound okay? Do you need me to keep going or are you good? I don't know who asked for that. Grace, do you need me to keep going? Okay. Anything else I can explain? So the keys are yours to keep. The knowledge is yours to make sure you get. Do you understand what I'm saying? So you need to make sure that you understand what it is we're talking about here, because these problem solving skills, especially the trig, solving for the angles of elevation and for the values, your algebra 2 ones. The only ones I wish I'd done, I wish I had thought to put more quadratics on this. I wish I'd thought to put, but the algebra 1 problem solving, I've had such a good time going back through memory lane. Would you agree? Was that a no? All right. So here's what we're doing today. We're going to continue talking about our related rates. So there's a warm up there. Go ahead and make your group mates jump in and be like, oh, let's differentiate. I can't wait. Anthony, can you hear me? Okay, so two things. The PDFs of these are on Schoology, so you can go ahead and grab them if you need. And number two, I have your headphones. So you left them behind a couple classes ago, and I want to make sure that you know that they're with me. Okay. Sure, no worries. All right, ready? So when we're talking about our related rates, what's happening is we're going to put together all of our conversations of what that derivative means. So we started off talking about position, velocity, and acceleration. When we're looking at the rate of changes, we can look at our second derivative and compare how one thing is changing to in our first derivative, how one thing is changing to another. We can look at our second derivative by looking at how quickly is it changing compared to the change, right? So what is the rate of change of our rate of change? So when we're talking about our related rates, we find ourselves in a situation where we are doing a lot of implicit differentiation because we have X's and Y's. And then what we need to do is make sure that when we understand if it's asking us to differentiate with respect to T, that means that there's maybe that third variable involved where I'm talking about the change of each variable with respect to, what does T stand for? Yeah, with respect to time. So when I talk about differentiating this, I have 2y dy dt is going to be equal to 12x cubed d, yeah. So we're used to forgetting about that x because if we're differentiating with in terms of x, we have the dx, which is equal to 1, which goes away. So now all of a sudden we've got a lot of these, we've got more work happening because we're talking about x in terms of t. We're not done. Plus 6 dx dt. So what we've been able to do is we can talk about this equation talks about the relationship between the rates of change. So this equation talks about the relationship between my x's and my y's as a position. This equation talks about the relationship between their rates of change. If I took a second derivative of that, I'd look at the rates of change of their rates of change. If I took a third derivative, it would be the rates of change of their rates of change of their rates of change. It could go on until I run out of variables. All right. If I was needing to find whichever function, my next step would then be to go ahead and solve for whatever it is that I'm missing. So if somebody was asking you for the rate of change of my x, I would factor this out and divide. If someone was asking me for the rate of change of my y's, I would divide by 2y. So my math is going to be dictated by whatever the problem is asking for. So if somebody's like, well, what do you do next? I'm like, I don't know. It depends on the problem. Are you okay with that conversation? All right, so now it says, now find dy dt when x is equal to 1, dx dt, and dx dt is equal to 2. Note that y is going to be greater than 0. So now I know what it is I'm finding, right? So I have 2y, and I'm looking for dy dt, and I have 12, and I have x cubed. Dx dt is equal to 2 plus 6 dx dt is equal to 2. I'm missing one critical part. What's up with this guy? Anybody have any ideas? Because if I'm solving for dy dt, I need to know what that value of y is. Any thoughts? They told me x. They told me the rate of change of x. So I was able to plug in x and its rate of change. Where do I get y? Thoughts? What do you think, Stephen? Yeah. So this equation tells me a story of input and output. So I know that y squared is equal to 3 times my x value, 6 times my x value. So that means that y squared is equal to 3 plus 6. Y squared is equal to 9. Y is equal to plus or minus 3. So if I have y is equal to positive 3 and negative 3, this is where you need to be a thinker. Because if you get a negative value for something like time or speed, you're not using it. Or distance. If you get a negative value for something like velocity or acceleration, then you can use it. So am I talking about this -3 or not? How do you know? Yeah, because weren't you curious? Why would they tell us this? So this is where you got to be a thinker. When you read that and they include that sentence, you're like, who cares? Why? Like, why did you feel the need to tell me that y has to be bigger than 0? Oh, I see it now. Because y is bigger than 0. See you later, Sally. So now I've got 2 times 3 dy dt is equal to, what's this? 12 times 2 is 24 plus 12. So dy dt is going to be equal to 36 divided by 6. The change in y with respect to time at that exact moment is 6. Now notice we don't have any units, so that kind of bugs me. But they didn't tell us what it is we were finding, so we're good to go. All right, so here's some guidelines when we're talking about solving these related rates pictures or these related rates problems. And be honest, when you looked at my key last class, did it make more sense? When I had pictures for each of the stories? When you looked at this key and saw that, now it's math class, not art, so forgive me. Did it make it easier for you to understand what was happening with this guy running? Did it make it easier for you to understand what was going on with this balloon? Did it make it easier for you to understand how this rectangle was changing? So we're going to get like really good at step number 1 is drawing a picture of what you see. Step number 2, when you approach this, is you're going to make a list of each of your unknown rates and quantities, and you're going to make sure you include units, because including units is going to be the thing that makes it easier for you to say which one goes with which one, and is this a rate? Is this an acceleration? Is this a velocity? When you relate the variables in an equation, that conversation has to be, what is the relationship between them? Looking at what operations are involved. You're going to differentiate with respect to time. And then you're going to be aware of any potential constants in each equation. The constant that might get you the most might be which one? What are the 2 constants that are disguised as variables? I heard E. Keep going. Pi. Yeah, E and pi are actually constants. So they're irrational numbers that mathematicians have discovered. And instead of, they can't conceptualize its value. So what they did was they put, like, think of it as like, what do you call it? And not an emoji, but we have the symbol for what an app looks like the icon, what's it called? Yeah, so like I show you like a little blue and white bird and you're like, oh, that's Twitter. What's that called? The icon? Is that what it's called? It doesn't sound right to me. The app logo? Yeah. So pi is the logo for 3.14159, blah, 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 blah. E is the button for that value. So make sure you know that those are constant. You're going to substitute your known quantities and rates and solve. Okay, so with your group mates right now, draw a picture. Talk about what equations are involved in these, in this first example. Go. All right, so let's go ahead and draw this. Some of you guys showed great motion. So let's go ahead and, are you going to come back or make me raise my voice even louder? Hello? Thank you. The width of a rectangle is increasing at a rate. So my dw with respect to time, it's increasing at a rate of 2 centimeters per 1 second. Its length is increasing, dl dt is increasing at a rate of 3 centimeters per second. So my length is getting longer and my width is getting wider. So we're talking about my rectangle changing? My width is getting wider, my length is getting longer. At what rate is the area, oh dear, of the rectangle increasing? So let's go ahead and talk about what the relationship. So this is one of the hardest things to talk about, because in the context of this problem, length and width have a special relationship. If I was talking about perimeter, it would be different. I'm talking about area. So I'm talking about relating these problems. I know that area is equal to length times width. The width of a rectangle is increasing. Length is increasing. At what rate is the area of the rectangle increasing when its width is 4 and its length is 5? What do I need to do to this value here? If I need to find the rate of change of the area, what do I need to do? What? Okay, I need to multiply this, but if I multiply 3 or 4 times 5, I get 20 centimeters. That doesn't tell me how much is changing. How do I know the rate of change? Say that out. Find the derivative. So the derivative of the area with respect to time is equal to, how am I going to differentiate this? What am I looking at? I'm looking at my product rule, right? So my first term times the derivative of my second plus the derivative of my first times my second. So when I take the derivative of a product, I'm super inconsistent with the order that I do it in. I'm sorry if that confuses you. But now do you see where a lot of these values are going to fit in? Do you have everything that needs to fit into this problem? Do you have the information? Because here's what's crazy. The rate of change of your area is going to be equal to whatever the length is at that given time times the rate that times the rate that the width is changing, plus the rate of change of the length times whatever the width is. With your partners, go ahead and agree on what gets plugged in where. And Marcus, that go. So here is a dynamic story. And what that dynamic story means, is that this triangle, I want you to picture clicking on this edge and pulling it out. And this length is getting bigger at a rate of 3 centimeters per second. This width is getting bigger at a rate of 2 centimeters per second. Imagine how hard it was for calculus students to understand this problem before any computer graphics and animation, right? Because when I tell you to click and drag and pull, you're like, oh yeah, I can totally see that, right? But think about how this area, this length times width is changing. At these two rates, given these two starting points, this area is changing at a rate of 22 centimeters per second. I assure you, friends, if you don't make sure you include units of what it is you're doing, you will not get full credit. I'll say that one more time. If you want full credit, you will not be lazy with your work. You will include units and you will make sure that you include, because those of you who have been leaving off this side of your equation, do you remember when you got so mad at me for taking off? Remember that, Tess? Remember that? Yeah. All of this matters. All of this matters. So you need to make sure that DADT, if you ever leave off this, the assumption is it's discontinued. So by not rewriting this, I'm assuming it's a conversation about area, not the rate of change of how the area is changing. Those are two very different things. Sound okay? All right, sorry about the back. Example 2. The student is painting the high school and standing at the top of a 25-foot ladder that sits perfectly against the wall. He's horrified to discover that the ladder begins to slide away from the base of the school at a constant rate of 2 feet per second. Okay, so, oh my gosh, this is like a horror movie. Let's draw this. Here's the side of the building. And this guy, for some reason, is on a ladder that's straight up and down. Isn't that what it says? Perfectly against the wall. So here he is hanging on. And we want to make sure we draw this head big enough so we can see the horror at which he's about to realize imminent danger. Anybody here an art student? Anybody here an artist? My sincere apologies. We can give him eyebrows and he'll be even more horrified. Oh! I told you I was taking a stick figure class, right? Did I tell you that?
Yeah.
They have a stick figure class online. Because what's happening is the base of the ladder is traveling this way. It's moving away from the school. All right. What do we know? We know that it's 25 feet. Right? It's just perfectly legible. It's horrified to discover that it's sliding away from the base of the school at a rate of 2 feet per second. So at what rate is the top of the ladder moving towards the ground when the base of the ladder is 7 feet away from the school? So when we talk about that triangle, keep in mind the constant here is the ladder. This A and this B are changing because my A is decreasing as my B increases. Are you okay with that? So let's talk about what equation relates these variables. Yeah, I heard it. Say it out loud, Stephen. Yeah. So I know that C squared is equal to A squared plus B squared. That's our good old Pythagorean theorem. Right? So in this story, this is our constant. Right? So I know that 25 is my hypotenuse, and that's equal to A squared plus B squared. So when I go to differentiate it with respect to time, 0 is equal to 2a, the change in A compared to the change in time, plus 2b, the change in B compared to the change in time. This is a kicker. Because that ladder is not changing. Now, unless you have one of those ladders that grows, you know what I mean? Where you pull on a thing and it grows, okay, then we can talk about a changing ladder. So don't, like, if you get one of those problems, just be like, I thought you said. So ladders can change, but only if they tell us about it. At what rate is the top of the ladder moving towards the ground when the base of the ladder is 7 feet away from the school? What do I see? What do I know? What do I need? What can I fill in? Let's talk about what I need. 0 is equal to 2. I need this value. I need this value. I need this value. I need this value. By the way, could I have like divided everything by 2 and just simplified? If you want to still do that, you can divide everything by 2, not a problem. Here's what I need to know. When this is 7 feet, do I have the ability to solve for that A value? Yeah? So I know that 25 squared is equal to 7 squared plus A squared. So 625, 49 plus A squared. 625 minus 49. Who's got a good brain for that? So here's the story that you need to understand. When this has a value, I'll do it down here. When this has a value of 7, this has a value of 25, and this A value has a value of 24. At that second, the height that the ladder is on the building is 24. Is that height decreasing or increasing? It's going to be decreasing. Don't be surprised if your rate of change is negative, right? So let's go ahead and fill in what we know. A is 24. Do I know dA, dt? That's what I'm solving for. The rate of change of the ladder. At what rate is the top of the ladder moving down? That's it. What is B? And how quickly is it changing? 2 feet per second. So negative 14 is equal to 24 dA dt. dA dt is equal to negative 14 over 24. Can I just call that 7/12? So therefore, the little 3 symbols, therefore, means that the change in my A height with respect to time is negative 7/12 feet per second. Why is it negative? Yeah. So this is growing, what's happening to this? It's decreasing. As my ladder that's against the side of the building is falling, this is decreasing, this measurement's increasing. Luckily, we record all of our classes and put the videos online, so he's not missing a moment of calculus. All right, with your partners, draw a picture, write an equation. You mark it, set, go. All right. So let me talk to you about what I drew and see if it makes sense to you. So that triangle formed by the ladder in the house, when the base is 7 feet from the wall, we already did that math, true? So don't we already know that this height is 24 at that moment? And then I've got a 25-foot ladder when it's 7 feet away. So I did all that math over here, so I'm okay with that, right? Okay. So what I want to know is find the rate that the area underneath the ladder is changing. Let's say that there's something under the ladder that I care about, whether it's being able to walk underneath of it or bushes or whatever. How is this shrinking, right? 1/2 base times height represents my area. Are you okay with that product rule? I group my coefficient with my B. So my first term times the derivative of the second plus the second term times the derivative of the first. Everybody okay with that math? So I know my base is 7. And I know my height is 24. If I'm looking for the rate of change of the area, where do I get dH dt? And where do I get dB dt? Yeah, dB dt is 2 feet per second. So I can fill that in, 2 feet per second. Where do I get dH dt? Isn't that what I just solved for? Right? Now granted here I called it my height, but isn't it also this A that I found? Right? So when I go ahead and stick that in, that's what I found. -7/12. Sound okay? So this 1/2 and this 2 are friendly, so they cancel out. So my change in my area with respect to time is -49/24 plus 24. So I can go ahead and do that math, -49 divided by 24 plus 24. Math, track. That's the rate at which my area is changing. So we usually try to tell kids that we always, especially when we have non-terminating decimals, to go ahead and go with the fraction. However, in the context of our problem solving, it usually makes more sense if we can represent things by rounding. So your rule of thumb will always be to round things to 2 decimal places. Therefore, the area is changing at a rate of 21.96 feet per second. It's square feet. Yeah. Part A. Don't I divide by 24? Did you find it? Good. No, that's okay. Thanks for asking. Billy, is your hand in the air? You're just, okay. All right, are we good? Let's talk about C. Find the rate at which the angle, uh-oh. Uh-oh, what's happening with angle? Yeah, let's bring out some trig. Find the rate at which the angle between the ladder and the wall of the house is changing when the base of the ladder. So let's see what angle we're talking about, because if I have 7, 24, and 25, obviously not drawn to scale. Please don't make me talk over you. So when we're talking about the angle between the ladder and the wall of the house, are you okay with this being our theta? Yeah? Theta is whatever angle we're talking about. So our sine, our cosine, and our tangent. Are you a SOHCAHTOA person? I'm a some old hippie. Some old hippie caught another hippie tripping on acid. And so cute, when I used to say that to my 8th graders, they thought like tripping meant like they fell over. So then I changed it to apples, and they thought that was better because he was tripping on apples. You're sweet, little 8th graders. Aren't they sweet? Yeah, I used to say someone hippie caught another hippie tripping on apples, and they bought it. The innocence of youth, right? Okay. Find the rate at which the angle. What do I know? Which trig relationship am I talking about here? You can use whichever one you want. Because you have all the, because you're not missing any of the, you're not missing all the data, right? So you got to pick one. Except for, this is a constant. Is this changing? So we're going to go ahead. I bet you we could use any one of these. Let's do this. So if the sine of theta is equal to my opposite over my hypotenuse, if I go to differentiate this equation, what's the derivative of the sine? Cosine of theta d theta dt. You ready? Would you mind if instead of using opposite, we used x? Do you see why? Anybody want to sing a song? Low d high dx dt minus high d low. You're doing great. Keep singing. Square the bottom. And away we go. If I'm looking for the cosine of theta, the rate of change, let's fill in what I know. Here's the cosine of theta. I can go find that. Right? Except remember this h is our hypotenuse. So this is going to be the change in. So we got to be careful that we don't screw up our variables here. Because we have this is our A and this is our B and this is our C, right? And there's our theta. So when we talk about the cosine of theta, maybe we should have called that our B. And then our H is actually our C. So that we know that we have our low and our D high is dB dt. Just to keep it straight. Because then we got to keep track of, because this DH needs to be this one. Yeah. Yeah, 25 is a constant, but wouldn't that just then be 0? Find the rate at which the angle is changing. So if we talk about this angle changing with respect to that, we should be okay. Because this is our constant that doesn't change, right? And here's why I want to try sine to see if it works. Because this whole away did tangent. And when you take the derivative of a tangent, it's so complicated. So because then you have the two rates. I don't think we need the two rates. So I'm seeing. So this cosine of theta, we're going to need to find out. So we need, so the cosine of theta, when my adjacent is 24 and my hypotenuse is 25. So we need to know the angle that has that. So we know the cosine. And that's going to give us our theta. So that's when you go into and you make sure your mode is in degrees. And you ask the calculator the cosine, what angle has a cosine of 24 divided by 25? And it'll tell you that's a 16-degree angle. So my theta angle measurement is 16.26 degrees. So that's what goes in here. So C is my 25. My rate of change of B compared to T goes all the way back to my 2 feet per second, right? Our B is our base, that's times 7. The rate that C is changing is 0 because that's a constant. And this square the bottom and away we go is this value here. So this is 0. So I have d theta compared to time is equal to 50 feet per second divided by 625. That's divided again by 16.26. So I have 50 divided by 625 divided by the change in theta with respect to time. Degrees per this is degrees per second, so it's going to be the rate at which the angle is degrees per second. Right. Cool. Right. Yes. All right. So our next day together is that cell day. Do you know what I'm talking about? So are you going to be here? All right. So we have 5, 10, 15 minutes left. We're going to start our activity.